of 25th PMO Philippine Mathematical Olympiad national stage, day number 1 and day number 2, 2023. Okay, there are 4 problems in each day. The time is 4 hours and a half, 4 problems like this, and for day 2, we have again 4 hours and a half for time, and we have 5, 6, 7, 8. Again, 8 problems. Okay, so we will solve geometry problem, combinatorics problem, number theory problem. I try to not only solve the problem, we want to analyze the problem, we want to see similar problems or what, and how we can approach a problem. So let's start solve first problem. And the ideas here we use are useful also in BMO, British Mathematical Olympiad, USAMO, AME, other math exams, IMO also. The problem says find all ordered pairs AB of positive integers such that a squared plus b squared plus 25 equal to 15ab, and a squared plus ab plus b squared is prime. So first thing when you see this problem, it's good to try to check some small examples. For example, a1, b1. Here it doesn't. For example, if a1, b1, right side will be 15. But for example, if one of them b2, for example, a2, b1, or vice versa, right side 30, left side also 30. And here, 2 squared plus 2 times 1 plus 1 is 2 squared 4 plus 2 times 1. Let's check. So first, we will see 2 squared plus 1 squared plus 25. We should check, is it equal to 15ab times 2 times 1? We will see this one is 4 plus 1 plus 25, 30, and this part is 30. So the assumption is satisfied. And let's see, is it prime? 2 squared plus 2 times 1 plus 1 squared is 4 plus 2, 6, 7. It's good. So we found one answer, 2, 1. And because the problem is symmetric with respect to A and B, you can say A is 1, B is 2. So we found 2 answers so far. You can check other small cases, for example, A2, B2, and you will understand that, for example, A and B shouldn't have common factor. They should be relatively prime, but they are not needed. They are only considering a small example. Then you can have a good intuitive thinking. But for solving this, we should also pay attention to some other things. So a small example is always good in many problems. Then you can have a good view of that problem. The other thing that we should pay attention. Okay. Here, a squared plus b squared plus 25, the first assumption, equal to 15ab. And our prime number is a squared plus ab plus b squared. When we have a squared, b squared, ab, we have a good changing variable. And also in SMT, Stanford, Harvard Math Tournament is useful at the end of the solution of problem number 1. I will write some homework that you can solve related problems in Stanford and some other exams. Pause the video and try to think which changing variable is useful. If we define S sum equal to A plus B and product, we write P most of the times, but here, let's consider, for example, let's define it as Q. This one prime. Product is AB, okay? Now, here we have a squared, b squared. We have a famous identity. You should know that a plus b whole squared is a squared plus b squared plus ab, 2ab. So we can consider that s squared here equal to a squared plus b squared, 2ab equal to 2 times product is 2p. Now, if you write first equation, again, let me call this 1. So, from 1 and from star, a squared by star, a squared plus b squared is s squared minus 2p. So s squared minus 2p, or this part that is here, plus 25 equal to 15ab, which is 15p because ab is product. And then q is what? Q is a squared plus b squared again. Here we have s squared minus 2p plus ab plus p. So it will be s squared minus p. Now from this part you can say s squared plus 25, or we can write s squared plus 25 equal to 2p negative 2p. We take it to right side, 2p plus 15p 17. Now here you can write s squared in terms of p or p in terms of s squared. You should check both of them. Maybe you ask, how can we understand we should replace what in terms of the other one? You should check all of them. You have time and you should check all of them. If you check s squared in terms of p, you won't reach any useful things. But if you replace p in terms of s, find p in terms of s, and replace in the other one, if you divide both sides by 17, s squared plus 25 over 17 equal to p. Now here, s squared we have here minus s squared plus 25 over 17. And then we can use common denominator 17 equal to 17s squared minus s squared minus 25, which will be 16s squared minus 25. And it's so much good because subtraction of two perfect squares. Now we multiply both sides by 17, so 17q equal to 16s squared minus 25. We have a famous identity that says, for example, x squared minus y squared equal to x minus y. You should memorize this. Also, we have some other identities for factorizing and some other things that are basic. So here 16s squared, we know that is equal to 4s whole squared minus 25 is 5 squared. So it will be 4s minus 5 times 4s plus 5. Now we have factorization, and it is 17q. We know because the problem says a plus b positive, so s is a plus b, a and b are positive, so it is at least 2. So here each part is positive because y for the product is positive, 17q prime numbers. 4s plus 5 positive because it is at least 4 times 2 8 plus 5 13. Here 4 times 2 8 minus 5 3. Okay, they are positive. And also because it is plus 5, it is greater than this. Now, if we want to check the cases, this one can be 17q, this one can be 1. Because q is prime, you can divide into numbers. 17, other case 17q, the other one q17. And yes, we have only these cases. So, let's consider these three cases. Case 1, case 2, case 3. In case 1, 4s minus 5 is 1. And 4s plus 5 is 17q. So from the number, always one of them is number. From that number, you can find s. So you say 4s, we add by 5 is 5 plus 1, 6. It's contradiction because here we have contradiction because 6 is not multiple of 4. If you consider case number 2, 4s minus 5 is q. And 4s plus 5 is 17. If we subtract 5 from both sides, 4s equal to 12, so s equal to 3. And here, if we check 4s minus 5, it's 4 times 3, 12. 12 minus 5, 7. 7 equal to q, so our prime number is q. Also, we knew that p is s squared plus 25 over 17, the product. P is s squared plus 25 over 17. We will reach, I guess that we will reach again a1, b2, a2, b1. Why? Because q is 7. In that case, also prime number was 7. So p, the product, s squared is 9 plus 25 because s is 3. 34, I'm sorry, here, 25. 25 plus 9, 34. Why I've written, let me correct this one. 25 plus 9, 34 over 17, 2, p is 2, the product. So product is 2 and sum is 3. So ab is 2, a plus b is 3. So because a, b is 2, a and b are positive integers, one of them 1, one of them 2. 1, 2, 2, 1, and it satisfies the sum. So it is exactly the case that we found. Again, draw rectangle around this. Let's consider last case. In our last case, case number 3, here, 4s minus 5 is 17. 4s plus 5 equal to q. This part. Again, if you add 5 to both sides, 4s equal to 22. 22 is not multiple of 4. Okay, so we don't have any answer here. As first homework, Stanford Math Tournament SMT 2019, you can solve x plus y 2, x4 plus y to the 4 equal to 1, 2, 3, 4. Around, I can say 1 year ago, I released the solution of this problem. In that problem also we should use Newton's sum and paying attention to same changing variables. Sum equal x plus y and xy product. So try to do it as first homework. Also, I released another video again around 1 year ago from Stanford 2022 Stanford Math Tournament or SMT. We have x squared plus y squared equal to 11, x cubed plus y cubed equal to 20, x to the 4 plus y to the 4 equal to 23, x to the 5 plus y to the 5 equal to negative 25, and we wanted to find x to the 6 plus y to the 6. Again, for also this problem, I've used s, the same changing variable that we used in this problem, s equal to sum, and p equal to product, and Newton's sum, some other ideas. Okay, if you want to learn more things, learn more ideas, important changing variables, important ideas when we see similar equations, if you want to learn them, feel free to send message to my WhatsApp number in the description and comments. Second problem of PMO 25th National Stage Day 1. It's 2023. We want to solve second problem. This problem was similar to a problem in a book for Maryam Mirzakhani. Let me tell you the problem. It is, I think, for around 15-20 years ago, the book. The problem is exactly similar, and the idea, the solution also similar. The problem was this. 2 to the p minus 1 over p is perfect square, and p is odd prime. Prime number and find all p. So I will solve problem number 2 for you, and by the same way you can solve this problem as homework, okay? And you can comment your answers right below this video, or if you had question, feel free to send message to my WhatsApp number in the description and comments. Okay, let's work on this problem. It says 2 to the p plus 1 minus 4 all over p is perfect square, so it is x squared. At first, let's check some small prime numbers. For example, if p is 2, it's 2 cubed minus 4 small examples over 2, 8 minus 4 over 2 is 2. It's not perfect square. If we check, for example, p3, then 2 to the 4 minus 4 all over 3. 16 minus 4, 12. 12 over 3 is 4. It's perfect square. So one good prime is p3. For example, we can check p5. It will be 2 to the 6 minus 4 over 5, which will be 64 minus 4, 60 over 4. Over 5, 60 over 5 is what? Is 12. It's not good. So let's consider general case. You say 2 to the p plus 1 minus 4 is px squared. We can consider p is odd, and left hand side is, we can say p is at least 7 because we've checked up to p5. So left hand side is multiple of 4 because 2 to the p plus 1 multiple of 4 minus 4 multiple of 4. This p is odd, so right hand side is multiple of 4. So we can say 4 divides left hand side, which is 2 to the p plus 1 minus 4. Also 4 divides right hand side, 4 divides px squared. Because p is odd, you can cancel p by Euclid's lemma, you can say. We call it Euclid's lemma when something divides the product of two things. Then, and 4 and p are relatively prime, we can cancel p. 4 divides x squared. So x is even, okay? And we can say, okay, x, for example, is 2y. So let's rewrite it to the p plus 1 minus 4 equal to p. Instead of x, I replace it with 2y whole squared. It is 4py squared. If we divide both sides by 4, then it will be 2 to the p minus 1 minus 1 equal to py squared. From here, it will be exactly same as previous problem. 2 to the p minus 1 all over p. So here we factorize because p is odd. P we said is at least 7. P is odd, so p minus 1 is even. So you can factorize left hand side 2 to the p minus 1 over 2 minus 1 2 to the p minus 1 over 2 plus 1 is py squared. When we have product of two things, this problem is also the idea we want to solve. This problem is useful in BMO, British Mathematical Olympiad round 2. I think around 4 years ago we had same idea. Let me find the problem. The problem is for BMO 2017-2018. The idea is exactly same. This idea because it's so much famous. Let me copy the problem. There's the problem here. Okay, PMO 2017-2018 round 2. British Mathematical Olympiad. Try to solve this also as homework number 2. Because the idea is same. So when we have product of two things equal perfect square or prime number times perfect square, you should consider GCD. So we consider GCD of 2p minus 1 over 2 minus 1 and 2p minus 1 over 2 plus 1 equal to d. Because d divides 2p minus 1 over 2 minus 1 and d divides 2p minus 1 over 2 plus 1. So if we subtract, d divides 2. And because the two numbers are odd, because p is at least 7, so it is even minus 1 odd, even plus 1 odd. D is odd, so d is 1. Okay, so they are relatively prime number. And because of this, we have two cases. 2 to the p minus 1 over 2 minus 1 is p, for example, z squared. One of them should be pz squared. The other one should be w squared because they are relatively prime. Or we can say the first one, minus 1 is, for example, c squared. Or do we have a or b? We don't have a or b. Okay. So the first one, for example, is a squared. 2 to the p minus 1 over 2 plus 1 is pb squared. Okay, for this case, if you consider mod 4, let's consider, for this one, let's first analyze this one. If we consider this one, we know p is at least 7. So p minus 1 over 2 is at least 7 minus 2, 6 over 2, 3. So if we consider mod 4, right hand side, because it is perfect square, is 0 or 1, a squared. It's easy. If you consider mod 4, a number, for example, t, is 0 plus minus 1 or 2 mod 4. And if you raise to the power of 2, it is 0, it is 1, it is 0. So 0, 1. Left hand side 2 to the something greater than equal 3 is 0 mod 4 minus 1. So it will be minus 1 is 3. 4 minus 1, 3. So here we reach contradiction. Now let's consider this case. For this case, we say 2 to the p minus 1 over 2, this one. Let's consider it is first one, it is second one. By second one, we say, okay, 2 to the p minus 1 over 2 plus 1 is w squared. If we subtract 1 from both sides, 2 to the p minus 1 over 2 is w squared minus 1. So it will be w minus 1 times w plus 1. Okay. Now here, because again we consider GCD. Suppose GCD of w minus 1, w plus 1 is d1. Then we can say d1 divides 2. Why? Because d1 divides w minus 1, w plus 1. If we subtract d1 divides 2, so d1 is 1 or 2. Because d1 is 1 or 2, so we know because the product is power of 2 and p minus 1 is over 2 is at least 3. So If the GCD is 1, they should be powers of 2. For example, it is 2 to the A, 2 to the B, because the product is power of 2. So if GCD is 1, the smaller one, we know a smaller one is this, should be 1. So it should be 1, then if it is 1, W minus 1 is 1, so W is 2, so W plus 1 is 3. It's contradiction. If GCD is 2, so this one should be 2, the next one should be another powers of 2, so W minus 1 is 2, so W is 3, W plus 1 is 4. So 2 times 4, 8. So 2 to the P minus 1 over 2 equal to 8, which is 2 cubed. So P minus 1 over 2 is 3. So P is 2 times 3, 6 plus 1, 7. Okay, so P is 7, and 2, let's check it. Let's check P7 here. 2 to the 8 minus 4 over 7. It will be what? 2 to the 8 minus 4 over 7. It's multiple of 4. So, you can factorize, or you can say, okay, 1 to 8 minus 4 over 7. 1 to 4 over 7. And you can say it is 1 times 7. I'm sorry, 2 to the 8 is 256. Let me replace 256, 252. 252 over 7, if you divide it with 3 times 7, 21. 42, 36. It is another perfect square, so P7 also works. So we proved that except P3 and 7, there is no answer for this problem. Also, this problem of the book, I can say the problem is repeated, because the only thing here, the difference between this and this, here, if you multiply this one by 4, you will reach this. And if a number is perfect square, it is equivalent that 4 times that is perfect square. So it is a repeated problem from a book with a small difference only multiplied by 4. So there are some books, some ideas. Let me tell you, the book has how many important problems in the first part? 72 problems. If you solve 40 of them, they are so much useful and have lots of ideas. If you want to know the problems of the book and important ideas like the things we've solved here, and I told you also in BMO round 2, the problem is useful. If you want to learn these things, as I said before, feel free to send message to my WhatsApp number in the description and comments. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. Problem number 3 of PMO National Level 2023 Philippine Mathematical Olympiad. Let's read the problem. It says in triangle ABC, so let's draw it. In triangle ABC, AB is greater than AC, like this. Point P is on line BC such that AP is tangent to its circumcircle here. And let M be the midpoint of AB, this part. And suppose the circumcircle of PMA meets line AC again at M. Okay, we consider PMA, circumcircle of this black circle of PMA, it says meets line AC again at M. Okay, if we consider this, we can say that this black circumcircle meet again AC at N. Also, we've drawn circumcircle of PMB because the rest of the problem we need that. It says then point Q is a reflection of P with respect to the midpoint of B segment BC. Okay, we've connected P to MN, and here K supposes midpoint. P is reflection, the problem says. Q is a reflection of P with respect to midpoint of BC. We consider midpoint of BC, for example, PK. And then it says the line through B parallel to QN meets PN at D. Okay, we draw QN, we draw a line parallel to QN through B. It meets PN at D. Okay, and the line through P parallel to DM meets the circumcircle of PMB. Again at E. Okay, we draw this line. DN, it is, for example, E. So show that the lines PM this line, BE, this line, and AC are concurrent. Okay, before solving this, I want to tell you Siwa's theorem is what? Let me explain for you here. Suppose we have a triangle, for example, ABC, and we draw three lines. We want to see under what condition these three lines are concurrent. It is A, it is B, it is C, D, E, F, A1, A2, C1, C2, B1, B2. For example, clockwise like this. Then, by Siwa's theorem, we know that sine A1 over sine A2 times sine C1. Look, A1, A2, C1, C2 times sine B1 over sine B2 is 1. If it is 1, it is equivalent that AD, BE, CF are concurrent. Okay, let me tell you another thing. Ratio lemma. The next part is also important. Ratio lemma. It says if we have a triangle ABC and if we draw a line like this, if you have A, B, C, P, 1, 2. So if you use two sine law in these two triangles, you can conclude, for example, in first triangle ABP, sine A1 over BP equal to sine B over AP. Also, you can say it is equal to sine P1 over C. If we consider triangle APC and consider again sine law here, sine A2 over PC equal to sine C over AP equal to sine P2 over B. Now, if we divide, let's consider first only the first two fractions. Sine A1 over, let me write it like this, sine A1 over BP equal to sine A2 over sine A2 over PC equal to sine B sine C. AP will be cancelled, so sine B sine C. So here we can conclude sine A1 over sine A2 equal to here BP over PC times sine B over sine C. If we consider first fraction and third fraction, instead of B sine B over sine C, we can write B over C, BP over PC times B over C. And we call this ratio lemma, and it's so much important to memorize this in many problems. AMC, AME, USAMO, and here PMO. It's useful, okay? Now let's analyze the problem. We want to prove, let me show you the three lines BE. This one and this one are concurrent. So let me show you the lines that we are working on. This line, and this line. We want to prove these three lines in which triangle? This one, this one, this one, ABP. We want to prove they are concurrent. Now, if we use at first, we should find this angle over this angle, this over this over this. The product of them is 1. Then by Siwa's theorem, we can say these three lines are concurrent. So let's see. This angle, it is tangent. So by tangent chord angle, it is half of this angle. So it is also equal to this one. It is B, so it is B. Now this angle is also A, so it is good. We found these two angles. Now, if if you consider this one, we can say it's P1. It is P2. So AB 1, 2, 1, 2. Okay, we want to prove y. Sine A over sine B times sine P1 over P2 times sine B1 over B2 y, it is equal to 1. Sine P1, sine P2 here. For finding this, I use ratio lemma. By ratio lemma, look, let me show you. We said sine A1 over sine A2 here is BP over PC times sine B over sine C here. We said, okay? So if we apply it here, sine P1 over sine P2 in which triangle? APB equal to AM over MB, which is 1, times sine A plus B over sine B. Okay, these two things are equal. And one important thing is sine 180 minus alpha equal to sine alpha. If two angles equal to 180, sine of them equal. So A plus B plus C is 180. So sine A plus B equal to sine C over sine B. So that is so much good because we found sine P1, P2 in terms of sine C and sine B. So next step we should calculate sine B1, B2. Here, if we want to find B1, B2, B2, let's consider it is alpha. We consider B2, angle B2 equal to alpha. But it is not related to this alpha. Let me just consider this beta, beta. So here it is alpha in triangle in blue circle. It is this arc, okay, B2. So we can say that which angle also this arc, this angle. Okay, so we can say this one inscribed angle, half of the arc is alpha. Because it is parallel to this, so it is alpha when we have two parallel lines. And a line intersect, we know if it is, for example, alpha, it is also alpha. So because it is alpha, this one is also alpha. So B2 is alpha, B1 is what? B1 is B minus alpha, okay? Angle B minus alpha. Now let's do a little angle chasing. We know that APNM is cyclic, okay? APNM is cyclic. So this angle, let me show you. APNM. These 4 points lie on the black circle. It is A plus B, so this is 180 minus A plus B. So this angle is C. Okay, it is C. So let me consider this one. This equals C. Now, another part, I want to find this angle. So if I want to find this angle, I can say again, this point, this point, this point, and this point are cyclic. So it is A, it is also A because they see the same arc. Okay, so let's write this angle equal to A. It is A, it is C, so this angle equal to B because we know in triangle MPN, sum of angles equal to 180. When it is A, it is C, it is B. So because it is alpha, we conclude that this angle is B minus alpha. Okay, so it is like here, alpha B minus alpha, alpha B minus alpha. So when I want to find sine B1 over B2, I can use triangle MPN and use ratio lemma. So sine B1 over sine B2 that we want to find here is sine B minus alpha over sine alpha. And if we use ratio lemma in triangle MPN and ratio lemma that I've told you, we can say d minus alpha over alpha is nd over dp times sine c over sine a. So let's write nd over dp times sine c over sine a. Now all things are good. P1, P2 we found. It is sine C, sine B, sine A, sine B. Here sine C, sine A again. It's good. So let's replace here. We should prove sine A over sine B. Let's consider this part 1, this part 2, and this part 3. By first one, second one, and third one, we should prove that sine A over sine B by second one instead of first and second, instead of sine P1 over sine P2. We write sine C over sine B times sine B1 over B2 here by third one is nd over dp times sine C over sine A equal to 1. So here we can cancel these two things and we should prove that y sine C squared over sine B squared equal to, we want to prove it, dp over nd. So let's focus here, dp nd. Now by Thayer's theorem. Thayer's theorem is what? Let me tell you. I told you Siva's theorem, ratio lemma. Most of you know Thayer's theorem. It is so much basic. And the proof is by similar triangles. It says if you have A, B, C, and D is parallel to BC, so if these two triangles are similar, we have two relationships. One of them here is useful, and we call it Thayer's theorem. AD over DB, look, this length over this length equal AE over EC. The proof is easy. You can use these two triangles are similar. ADE is similar to ABC. So we can say AD over AB, ratio of corresponding sides equal to AE over AC. And then you can say AD over, in fractions we can do this, AB minus AD. Look, denominator minus numerator, you should do the same thing on right side. AE over AC minus AE, okay? So it will be AD, AB minus AD is DB equal to AE, AC minus AE is EC. Okay, now if you use it here, let me tell you in which triangle. If you consider this triangle, this one, okay? Let me show greater one. This, in this triangle, and for this line. Because these two are parallel to each other, we can say ND over and DP over. ND is what? Is PB over BQ. So let's write DP is PB. Instead of ND, you can write BQ. So we should prove this. Now if you see, PBQ are not related to all these points. So let's, when you see something like this, try to erase all things that you don't need. Okay, here in this part, we want to prove only what? PBBQ. So the only thing we need P and Q. So we don't need this triangle. We need only this circumcircle. We don't need this. We don't need this. Let's erase all things that we had. Circumcircle we need. It is the midpoint we need. So let's erase also these parts. This one, this one, this one. Okay, it is so much useful when you don't need, for example, these things. It's better to erase them. You can prove it with an easier way. So K is midpoint, so it is equal to this, and Q is reflection of P with respect to K, so it is equal to this, because this part equal this part, and K is midpoint, so the remaining parts are also equal. So you can say it is A half, it is A half, it is X. So because it is equal to this part, it is also X. Now let's see that we should prove what? We want to prove PB over BQ. Let's write PB over BQ. Why it is equal to sine squared C sine squared B. Sine squared B. Now because PB is what? PB, you have here BQ equal to PC. So we can say PB over BC. So because we have this, so we can also erase Q. PB over BC. Let's check again. PQ, PC, I've meant. So let's erase this part. PC. Y is equal to sine squared C over sine squared B. So here we don't need these midpoints. We can erase this part. We can erase these. So here we should prove that y PB over PC equal to sine squared C sine squared B. I want to use ratio lemma, okay? A1, A2, we said sine A1, A2 is BP over PC times sine B over sine C. Or B over C. I want to use this ratio lemma, but P is outside. Here P is inside PC, here P is outside. So if I use ratio lemma, I say okay, P is outside, so this angle over this angle. It is what? It is now our A1, it is our A2. Sine A1, again, if you can prove this ratio lemma again by 2 sine law. It is equal to PB over A2 is what? PC times. When you say A1 over A2, look, you should consider farther side. Here, when it is A1, A2, BP, if you want to say BP, PC, farther side is B with respect to A1 for A2, C. Now here, when you want to write, you say, okay, A1, A2. Farther side is here, B, C. For A2 is C. Okay, so you write C, and for A1, it is what? B. For one of them, that's A1 covers all of them. For A2, the farther side is C, and for next one, write B. So sine A1 is what? Sine A1 is A plus B. Sine A plus B. And as I said, you can prove it with 2 sine law, ratio lemma. Sine A2 is what? Is B. Sine B equal to PB over PC times B over C. We can write sine B over sine C. Now A plus B plus C is 180, so it's equal to sine C sine over sine B. So we can say PB over PC equal to, you can take sine C here, it will be in numerator, sine squared C over sine squared B. So we proved this part. Because we proved this part, then this part will be okay, and then the Siwas theorem will be okay. So we proved that it is one, so by Siwas theorem, these 3 lines are concurrent, and we proved this problem. Okay, so as you can see in concurrency, Siwas theorem useful. Learning how to work with ratio of signs useful. Ratio lemma so much useful. Phase theorem useful. For example, we have some ideas like ratio lemma. We can call some of them for ourselves double Pythagorean theorem. That is also so much useful in any problems, AMCU, SAMO. If you want to learn these 40-50 important ideas, background ideas, formulas, feel free to send message to my WhatsApp number in the description comments. PMO 2023 National Level Philippine Mathematical Olympiad, problem number 4. Last problem of first day. It says in chess, a knight placed on a chessboard can move by jumping to an adjacent square in one direction, up, down, left, or right, then jumping to the next two squares in a perpendicular direction. It means this. If you don't know chess is what? For example, if you have knight here, if you have knight here, for example, 2 units here, one perpendicular to this part. 2 here, one perpendicular. Or for example, 2 here, one perpendicular. This one. And this one. In general, it can go to these 8 points. Okay? Jumping for, so it says to an adjacent, then 2 perpendicular, to an adjacent, 2 perpendicular, to an adjacent, 2 perpendicular, like this. Then it says, we then say that a square in a chessboard can be attacked by a knight if the knight can be end up on that square after such a move. So these 8 cells can be attacked by this knight, okay, here. Thus, depending on where a knight is placed, it can attack as many as 8 squares. So in general, it is 8. But for example, if it is in the corner, like, let me show you. If it is in the corner like this, then if we consider, it can attack, for example, only 2. Here and here, because the other 6 cells are outside the square. In a 10 by 10 chessboard, what's the maximum number of knights that can be placed such that each square on the board can be attacked by at most 1 knight? For these types of problems that you want to find maximum or minimum of something, you should say answer is at least what, at most what, and one part is by example, one part is with proof. So which part is by example? Try to say by yourself. This part, for example, if you find an answer 6 that it works, you understand that the answer is at greater than equal this, and this part is with proof. So you can check some small examples to guess the answer, and you can check something. Let's work on some examples. Let me tell you. Okay, let's consider one thing that I've done. I consider an example, and I said, okay, let's consider, and one idea, coloring. Look, we have 3 types of colorings that are important. One of them checkerboard scheme, one of them general form of checkerboard scheme, and the other one columns coloring. And for example, one problem of PMO national level, it's for 2021 or I think 2020, can be solved with checkerboard scheme. In UK, for example, round 1 and round 2 can be you can solve the problem by column coloring. 90% and also checkerboard scheme. This one is the most famous one and most useful one. 90% of the problems that can be solved with coloring can be solved with one of these 3 types, or sometimes 2 of them. Now let's consider this one. If you consider, for example, this style, suppose, for example, this one can be attacked with 2 knights. If you consider checkerboard scheme, it is this. In each move, when you consider a knight, the color will change. For example, when you come from black to white. Okay, so the color changes by each move. Now, the next thing we can say is we want to consider, for example, some knights. If you have, for example, a knight in black cell and a knight in white cell, they cannot attack a common cell. Why? Because it is in, for example, it is black also. For example, this one, and for example, this one that is white. Because when it attacks something else, this one is white. When it attacks something else, because it is white, it attacks something that is black. Okay? So we conclude that the whites and blacks are not related to each other. So we can work only on, for example, whites. Okay? So let me color changes. Okay, let's color with black and white. For example, this. And look, we work on, for example, white cells only, then multiply by 2. We want to find an example. So if we consider blacks, black, let's color them. Black, black, this one, this one, this one, this one. Okay, let's color. Okay, these things are black, black, black. This one, this one, this one, this one, this one. Okay. Now I consider this one and this one. So we know that they cannot attack anything. Also, we consider this one, we consider this one, we consider this one. So look, if, for example, two things can attack one common cell, it means that with two moves they can reach each other. Here, if you consider all possible moves, you cannot reach from this to this. And also, if you consider this one, from this one, you cannot reach. So 1, 2, 3, 4, 5. Let's see. They consider which cells that are bad. So this cell is bad because you can say that why this cell is bad? Because of this. I want to select these 1, 2, 3, 4, 5. These 5 cells, and I want to see which cells are bad. And we cannot place any knight, so we can see which cells are left. So for this one and this one, you say, okay, I go here and then here. So it is bad. We cannot use this. This one similarly is bad. This one similarly is bad. And for this one, you say, okay, I come here and here. So this one is also bad. Let's consider this one. You say we go here and here. So if the distance is 1, 2, horizontal or vertical, it is bad. So by this method, it is also bad. This one is bad. The distance 2 is bad because of this. For this one is bad. This one is bad. For this one, bad, bad. For this one, okay, we consider all bad. Now, next one. If you consider this one, it goes like this and this. So it is also bad. Now this one, again, you go like this, it is bad. So the horizontal like this, it is bad, similarly, it is bad. You consider it is bad, it is bad, it is bad, it is bad. Let's consider this one. You go like this and this. So this one is also bad. This one goes like this, so we cannot say this one is bad. But here it goes and it goes. It is bad again. This one, with this one, the distance is 2. So it is bad. The distance is 4 if you consider 1, 2, 3, 4. For this one, it's also bad. And if you consider this one, for this one, it is bad. For this one, it is bad. For this one, it is bad. And let's consider this one is also bad. Why? Because you go this and this. So this one is bad. What about this one? Again, this one also is bad. For this one, it goes here and it goes here. This one is bad. It goes here, it goes here. It's bad. This one, for example, this, it is bad. This one, it goes here, here. It is bad again. This one, they cannot reach to this part, okay? And what about this one? For example, this is bad. So, for example, this one. Can they reach here? Yes. It is also bad. What about this one? It goes here, it goes here. It is bad. What about this one? It goes here, it goes here. It's bad. Now, 2 cells are left here. We can select one of them, and they can't reach this one. So 1, 2, 3, 4, 5, 6. One more. And here, if you consider the cells that are left, let's consider also this one is bad because here, it is bad. So we have 2 cells here. So look here how many we can place here. You can select one of them. So 1, 2, 3, 4, 5, 6, 7, 7. So here we prove that the answer is at most or at least 7 times 2. You can use the same thing similarly for blacks, and it will be 2 times 7, 14. Now we want to check for again another example. Here I consider this direction. Now I want to consider this direction to see can we find any better example. Okay, now let's consider this table. And let's consider is this around this. Okay. Now, instead of this part, here I consider these things. Again, I will reach 5. 1, 2, 3, 4, 5. But this time is better. Because similarly, if we ignore, we said these two things we can ignore like this. So we can remove these cells. This one again, the distance 2. We can remove distance 2. Remove this one. And also distance 4 we can remove because of this move, this move. So distance 2 and 4. And this one also you can cancel, you can cancel. We can cancel this one. We can cancel this and this. So here, here. And this one. Okay. Now, because the horizontal, the diagonals adjacent you can remove. Why? Because this one. So we remove these cells, this cell, this cell, this cell, this cell. Now, if you want to consider this, you can go here, here. We can ignore this here. You can go here, here, or here. So we can remove this one and this one. This one you can remove. Let me check this one. Here and here. Okay. Here, here, we can remove this part. For example, this remove. And this one we can remove. This one we can remove. What about this one? We can remove. So these cells are left. They cannot reach here. What about this one? You can remove this, and you can remove also this one. For this one, we can consider this. We can remove it. For this one, you can remove this. Last one, you can remove this. Okay, but we cannot reach here. Now, here we can select this and this and this one. So how many cells? 1, 2, 3, 4, 5, 6, 7, 8. So we prove answer is at least 2 times 8, which is 16. Now we want to see, can we prove the answer is at most 16? Now here we divide the square into 4 parts. 1, 2, 3, 4, 5. Here we draw this one. 1, 2, 3, 4, 5. We divide this part. And now we proved the answer is at least 16. If we prove the answer is at most 16, the problem will be solved. Okay. So how can we prove this? If we prove in each part, we can place at most how many? We can say the answer is at most 16. If we can prove it, we can place at most 4. So let's see here. As you can see, we should prove the in each part we have at most 2 in white cells, and also at most 2 in black cells. In general, at most 4. So if I consider the whites here, we want to see, can we place 3 or more? If we place 1 here, for example, then we go here. Let's see, we can cancel which of them. We can cancel this one because of this. We can cancel this one. Because of this, we can cancel this one. Similarly, we can cancel this one. We can cancel this one by this. And we can cancel this one. 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 So if you place here, you can select at most 2. So we've considered this case that if you select this, we want to say that in white cells in each part is at most 2. We want to prove it. So if you select this, we prove this. So we don't consider this one. Now similarly also we prove this one, this one, if you consider from here. Now if you consider this part, if you place here, it is similar like as this. So we can say that, for example, we cancel this one because of here, and we cancel this one. Okay, so here, if we consider this one, we cancel this. If we consider this, we cancel this. We go here, we cancel this. We go here, we cancel this. Again, we can select at most 2. So we consider this case. Let's also cancel this one. It is similar to this one. Now for here, we can cancel these things, and also this thing, and only we can select this. So also we check this one, and it is similar to this. So Here, obviously, we can select at most one because all of them can bridge to each other by two steps. So we proved in this part it is at most two. Also, in this part it is at most two. But here it is a little different for white cells. Why? Because we have corner. Here, look, these two are similar, but these two corners were like this. Let's see, can we prove here it is at most two or not? So if we want to prove here, we say if we select this one, we can cancel this one. The problem here is what? This cell and this cell will be left. Okay? So, because of this part, we can say, someone can say we can select these three things. Okay, here. The only possible case that we have three I want to say is this. Okay? Let me prove it. If we don't select from these three cells, for example, if we select from here, we can remove this, remove this, remove this, remove this, remove this one. So let's consider we can remove which one? You can remove this, you can remove this one, 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 and these two. If you select these two have problem with each other. So here, if you select this, we can select at most two. So let's remove this part. Now, similarly, because it is bad, we can say this one is also bad. And if you select this one, here also, when you wanted to prove in this part, you should check both of them. Okay, this is similar to this one, this is similar to this one. Now, if you check this one, it can cancel this because you go like this, you can cancel this one because of this, you can cancel this one, you can cancel this one, you can cancel this one. Here, as you can see, we can select this one, this one, this one. Also, it is good. So, we should say that we have only these two parts, these two cases. So let's do something. We found only this case if we select here. So if we select, for example, something here, then you can cancel this one because of this. Then you can cancel this one, you can cancel this one, you can cancel this one, you can easily cancel these two things. You can cancel this one, you can cancel this one, and you can select at most two. So let's remove this. Similarly, we can remove this. If you select also this part, we can cancel this, we can cancel this, we can cancel this, we can cancel this, we can cancel this. So again, we can cancel this. Again, we can select at most two. Here, let's erase this part. Okay. Now we can say, okay, it is also bad. Similarly, it is also bad. This one also, if you select, you will see that this one is bad, not necessarily. You can cancel this one, you can cancel this one. Again, look here because these two cases are not necessarily bad. So you can also select this one, and this one. Okay, at most. So all cases are what if you want to check this, or let me write all of them. So one case that you can place 3 is this. One case that you can place, for example, suppose we have this corner, okay, and here we have something else. This, and the only other possible case is this, and this. Okay, we have from here it is our corner. So we have only these three types. So let's see if we can place. So here we proved answer is at most what? 3 here, 3 here at most, 2, 2, 3, 3, 6, 6 plus 2, 8 plus 2, 10. So the answer is at most 10 times 2, 20. So here we prove this. And it is 16. Because we considered twice something, the answer is 16 or 18 or 20. We should prove and we should see which is the answer. Okay. Now let me tell you an example. Here it is 1, 2. I've used previous part here that we have, for example, this, and this. So look, sometimes proof helps to find a better answer, or sometimes answer helps to prove a number that is better. If we consider these things, here we will see one problem here. So this part. This part, let's erase this one. 1, 1, 2. If we consider this part, if you consider this one, also this one is bad. Because look, when you have these two things, you cancel this thing, and this one by here, by here, by here. This one you can cancel this, and this one you can cancel this. What about this one? You can cancel this. This one you can cancel. This one you can cancel. So we don't have this example. So it should be, if we have 3, it should be this or only this. We have only these 2 cases, okay? Now let's analyze here. We know here we have at most 2, okay? Here also we have at most 2. So 2 plus 2. Here we want to see, can both of them be 3 or not? Let's erase this part. Look, if you want to have 3 here, it is this, or this one, this. And as you can see, for both of them, we cannot select this. Why? Because if we select something like this, then what is the problem? These 2 things have problem. So we have 2 ways. One way is to select one of them like this, one like this, and the other one like this. And this case again is also bad. So the other case, if we want to select 3, is for one of them. Let me select for one of them like this. For the other one also like this. So here we have 3, 3. Now let's see, can we have 2 here? When you consider this thing, it remove this one from here. Let's consider only this part. That effect on this part will be what? You can select this one, you can ignore this one, you can remove this one, remove this one. You remove this one, you can remove this one. What about this one? You can remove like this. You can remove this one, you can remove this one. And these 3 cells are left. And here we can select only one. So let's erase these parts. If in one of them we select something like this, then here you can select at most 1, because if you select, for example, any of them can reach each other, any 2 of them. So if it is like this, so for example, it is, suppose it is this type, or this one is this type. So here we have 2 squares. If we select like this, they cannot reach each other. So here, let's consider this is square S1, this is square S2. S1 and S2. If both of them be 3, so if they will be like this, it's not possible. Also, this part we said not possible. So if both of them 3, the only possible case is this. And when it is 3, 3, we can say here we have 1 case, here we have 1 case. So the answer is at most what? 2 times, because for black and white. 3 plus 3 plus 1 plus 1. 3 plus 3 plus 1 plus 1. It will be 2 times 8, 16 in this case. Now, if we have only one of them is this, and the other one, for example, has 2 at most. Okay. So, because of this part, we will see here we can have at most 1, at most 1. So, the answer will be at most 2. 3 plus 1 plus 1. Plus this part is at most 2. So 5, 2 times, in this case, it is at most 70. Now, what are the other cases? If here, one of them is like this, and the other one is at most 2. So let me rate. Okay, so here S1 is like this, and S2 is at most 2. So let's see here, it removes which cells? Removes this one, this one, and here it removes this one like this. And let's consider this part. We remove like this. And what are the other cells that we can remove? This one, this, and then this one. Okay, we cannot reach this, right? Okay, so we remove these cells, and by this one, we can say, okay, we remove this, we remove this, and again here you can select at most 1. in this part. Let's start here. 2 times 7 is at most 14, I've meant. So here again we can select one of them, because any two of them can remove the other twos. Okay, we can remove the other one. So here is at most 1. The answer will be at most 2 times 2 plus this one is 2 times 3 plus, here is at most 1, here similarly at most 1, 1 plus 1, and here is at most 2. So it will be 5 plus 2, 7, 14. Okay, so we proved if we consider all cases, the answer is at most 16. So we can say, okay, we've reached 16, and we proved both parts. So the answer equal to 16 for this problem. Okay, if you had any question, look, these things that you consider an interval, step-by-step, try a little, an example, try a little, and proof. We have many problems like this in PMO, and for example, USAMO 2023. I released the solutions of them. We had problems similar to this. If you want to learn ideas like this, problems can be solved with this idea, feel free to send message to my WhatsApp number in the description comments. We want to solve 25th problem of PMO, Philippine Mathematical Olympiad, Day 2 national level. Problem number 5. In this problem, we want to use an idea that useful also in IMO 2019, International Mathematical Olympiad, problem 5, second problem of day 2. Part A, useful invariant, these types of problem that, for example, say something stops. Also for BMO round to British Mathematical Olympiad, look, BMO is all BMO and USAMO. For UK and USA, these two national Olympiads are the most prestigious national Olympiads and so much useful for your CV. And as you can see, the last BMO round 2 2023 second problem, again, you should use invariant. Also for SUMAC, Stanford summer camps, there are lots of invariant problems. Look, you can solve these two problems as homework number 1, homework number 2. Also, if you wanted to learn more ideas in invariant, feel free to send message to my WhatsApp number in the description and comments. Now in this video, we want to focus on this problem, 5th problem of PMO. Let's read. Sileria is very happy for the 25th year of the PMO. In his jubilation, he ends up writing a finite sequence of A's and G's on a nearby blackboard. He then performs the following operation. If he finds at least one occurrence of the string AG, he chooses one at random and replaces it with GAAA. He performs this operation repeatedly until there is no more AG string. So it changes AG, he changes AG to GAA. It's our operation. Show that for any initial sequence of A's and G's, Sileria will eventually be unable to continue doing this operation. Okay. For this problem, we can use some small example on length, or for example on G, because we need G, and the problem says we change AG, I think, to G, yes. AG to G, 3 A's. So first, for solving this, pause the video and try by yourself as much as you can. Then see the video part by part as hint, because it's important to try by yourself. So first, we have AG. Here, if you have 1G, let's solve problem. I want to use a small example. The useful idea that in all exams useful also for IMO hard, you can solve hardest problem fast by this idea. You should find the idea, not only the pattern. A small example on what? You can use on length. I want to use a small example on number of G's. Okay, number of G's. So, if number of G equal to 0, it's obvious that you can't do anything. If number of G is equal to 1, means you have 1 G. Suppose you have some A's before. Suppose you have some number of A's before G and some number of A's after G. Suppose here you have N1, Here you have n2. Look, these n2a's are useless. Why? Because you can only change ag to g 3a's. So here in each step, if I apply this, I change, for example, this ag to g 3a's. And so how many a's are there here? It will be n2 plus 3. And how many a's are left here? n1 minus 1. So with each step, the number of a's before g will be decreased by 1. So how many times can we apply this operation? Can you tell me at most? Pause the video and find it by yourself in terms of n i's. Yes, it is n1, because in each step number of a's before g, it will be decreased. Now if number of g's be equal to 2, so number of a's here, if you have, for example, n1 before first g, then after first g and before second g, number of a's equal to n2. Then after second g, number of a's equal to n3. Okay. Now, here, I want to see how many times I can apply the operation on this g. Because I have only n1 before g, so I can do it at most n1 times. Okay. For this t, at most n1 times. Now for this one. How many times I can apply for this g? I have n2a's here. At most, how many times I can apply? And these n1a's, it should come after this g, and each time, each of them will be 3. When we move this, for example, when we have ag, you change it to g3a. So n1 will be at most 3 n1 here plus n2. So you can apply on this g n2 plus 3 n1. So it will be okay. Now you can solve it with induction. Now I consider, for example, number of g's is at most k minus 1. Or let's consider for number of g's, suppose k we want to prove, and suppose for 1 to for 0 1 to k minus 1 we proved. We want to prove for k minus 1. I want to prove for k, also for k minus 1, and with only k minus 1 we can prove. How? I say the number of a's here is n1. Without induction also you can say number of g's here n2, and so on. Okay. So the number of times you can apply on this g is at most n1. And so suppose, for example, you've applied on this g some number of times. For example, suppose by contradiction you are applying this operation on this sequence for infinitely many times. Because you can apply at most n1 times g, there is, for example, there is a step that after that you can't apply on first g. Okay, so first g you apply here, here, and you can apply for at most n1 times, and you can also apply on other g's. And then after that, you can say here, when you don't apply on first g, you have a sequence, okay, and you don't apply on first g anymore, we can ignore that. You have these g's, so you have some number of a's here, you have some number of a's here, g, and so on. It is, for example, first g, second g to kg. So it is first g that we can't apply, third g to kth g. Okay, here by induction, you can say that it will he will eventually stop after finite number of steps. Eventually stops after finite number of steps. Okay, and the problem has been proved because by induction, and we've used k minus 1 here because we have k minus 1. One way is this by induction. Another way you say, okay, on this g you can apply at most n1 times. On this g you can apply at most 3n1 plus n2. Then on next one 3 times this plus n3 and so on. So you can say the number of operations is at most what? Okay, so we've solved this problem by, we call it invariant. The problem that says something will stop. You can use these things. You can find a function or anything that you say, okay, it will be stopped after some number of steps. Or you can say we have a function that is increasing and f is integer. It is always greater than equal 0. So after some number of steps, it will be decreased. There are some techniques. And the functions are what? We have three important functions: sum of variables a1 to ak, sum of squares of variables a1 squared to ak squared, and another one, product of variables. These three functions are so much important. 90% of these problems that you need to solve are this. Another one that you should pay attention for this problem, leftmost G. Leftmost, rightmost also in many problems useful. Another thing that in invariant is useful is, for example, let me tell you, something you want to say is impossible. And for example, like what? You say plus minus 1, plus minus 2, plus minus 100. It is impossible to select plus minus to reach 101. The reason is what? If you calculate all of them plus, left side will be even. If you add plus to minus, change plus to minus, it will be also be even. And this part is also, it is impossible. For example, this one is considering mod 2. And also number theory useful. And we have three important colorings. And in BMO round 2, British Mathematical Olympiad, in IMO useful, in US IMO useful, three important colorings we have. Checkerboard scheme, general form of checkerboard scheme, and columns coloring. In general form of checkerboard scheme, we have two types: increasing, decreasing. If you want to learn important thing in colorings that are useful in BMO round 2, let me tell you the year: 2023, 2022, 2021. One problem is related to tiles and coloring, and you can solve that problem easily with the ideas that are in previous books and problems. Okay, if you want to learn invariant, that is so much useful in SUMAC. SUMAC is Stanford summer camp, Stanford summer camp in mathematics. There are lots of problems related to invariance, more than half of the problems. It's so much good for your CV if you want to apply for Stanford summer camp or Promise. It is another prestigious summer camp. I released some hints for the solutions of the SUMAC 2022-2023, also for Promise 2022-2023. Most of the problems in Promise were same. In SUMAC, some problems, the ideas were same. Okay, if you want to learn important ideas in invariant, number theory, geometry, the important formulas, and combinatorics, as I said before, feel free to send message to my WhatsApp number in the description and comments, and try to solve these two homeworks, and you can comment your answers right below this video, or if you had questions, send message to my WhatsApp number. And please don't forget to subscribe, turn on the bell, and like the video. Thanks. See you next time. Bye. PMO national level, Philippine Mathematical Olympiad 2023, problem number 6. It says find all functions f from real numbers to real numbers such that f of 2f of x equal to f of x minus f of y plus f of x plus y for all x, y that are real numbers. So look, when you see a function problem, there are around 20 important ideas for functions. You should consider special cases. You should consider, for example, small examples. Special cases means, for example, x equal to y, something like this. Special cases, x equal to y, x equal to negative y. Small examples means, for example, f of 0, something like that. Now, third one, get rid of complicated term here. We need that. How? For example, if we want to get rid of this, we change only y, and then this part will be equal, and we can get rid of that if you subtract the equations. I will show you in the rest of the video. Fourth rule that we have, there are lots of things. Check is f 1 to 1, 1 to 1, or injective or surjective. Surjective also good to useful. In 1 to 1 or injective means what? Means that you should check if f of x equal to f of y. If we can conclude x equal to y, then the function is 1 to 1. And we have also other things. Telescoping rule you should use in many problems. They are useful from, for example, round 1 from basic level exams when you see function problems up to IMO. Also, we solve IMO problems with these ideas. Telescoping rule, sometimes telescoping sum, or sometimes telescoping product. Lots of, I said around 20 important ideas. So let's start to solve this problem. Now we want to use the idea I told you, get rid of, for example, complicated term. How here we have two complicated term and our problem is here. So I say if we consider x and y, we have this. If we consider instead of y, we write w. So we have f of 2f of x. So we consider x and w. It will be f of x minus f of w plus f of x plus w. Now if we subtract, left side will be 0, right side will be f of x minus f of y. Look, here f of x again will be cancelled, so it will be f of x minus f of y plus y minus f of x minus f of w minus w. And f of x will be cancelled. So if we take these two things to left hand side, we conclude that f of x minus f of w plus w equal to f of x minus f of y plus y. So here we understand that. So we could get rid of this complicated term. Here we can say, for example, let's consider x equal to 0. Okay, if x equal to 0, again, look, considering a special case or small example, f of negative f of w plus f of w plus w equal to f of negative f of y. For all y and w, we have this. And now here, we can say, okay, for y0, for all wy, it is correct. So for y0, if y equal to 0, then we have f of negative f of 0 plus 0, which is, you can cancel this 0. We can call this one c. Okay, so our c is a constant equal to f of negative f of 0. So for all w, we conclude that f of negative f of w, for example, equal to c minus w. We want to analyze the problem, not only the solution. I want to see what are the maybe useful things we can reach, and at the end we should see which of them we can select. So don't be afraid that, for example, this point that we've reached is useful or not. We reach and write all things. For example, we reach 8 things, 5 of them useful, 3 of them useful. It's not important because first we know which of them useful. When we want to write in our answer sheet, we write at the end only the useful things. So here see, when we take w to right hand side, it's negative w. You can change w to x because it is only a variable. So the first thing here, f of negative f of x equal to c minus x. Okay, now the next thing from here, I want to prove that f is 1 to 1. One of the important thing I said, also check if is f 1 to 1. I say how we can check. Suppose f of x equal to f of y. I want to see, can we conclude x is y? Let's analyze. Because of this thing that we reached, and I call it 1, we know that f of x equal f of y. So from this part, we can say f of negative f of x also equal to f of negative f of y. Why? Because here, if f of x equal f of y, so negative f of x equal negative f of y, they are equal. And if we apply 1 here, c minus x equal to c minus y, we can subtract c, so negative x equal to negative y, so x, if we multiply by negative 1, x equal to y. So we conclude f is 1 to 1 function. Okay, it is the second important thing we've reached here. Now here, I know, so because f is 1 to 1, if f of something equal to f of something, that the thing inside are equal because f is 1 to 1. Okay, it is the importance of 1 to 1. And here, if I say y equal to negative f of x, I can cancel this, then I have f of two things, and I can use f of f is 1 to 1. So I consider y equal to negative f of x. And if I use this, left side is f of 2f of x equal to f of x minus f of, instead of y, I write negative f of x. And here, plus f of x. Instead of y, we write negative f of x. So we cancel this thing because f is 1 to 1. From second thing we've reached here, And I forgot to tell you something. Here, at first also it's good to try to check some special cases that does it work or not. For example, one of special cases, f of x is constant. If it is this constant plus y, it changes. So we cannot say that it works, but f of x, here it will be 2x, here it will be x minus y, x plus y, again 2x, so it works. Also checking some cases that works or not can be useful. Now here, because f is 1 to 1, we can say insides are equal. So 2f of x equal to x minus f of negative f of x. And for this one, by first thing we've reached, f of negative f of x is c minus x. So here you can say c minus x, so it is x minus c minus x. So it will be x minus minus x, 2x minus c. Okay. Now here, we can divide both sides by 2. And we can say f of x is x minus c over 2. We can define c over 2 as, for example, k. Okay. So it will be x as 2x minus c. So here it will be x minus k. Okay. Or let's do something. Consider k equal to negative c over 2. It will be x plus k. Now that we've reached here, f of x equal to x plus k, I want to again consider main equation. Okay, I reduce this. I say it is f of 2f of x. F of x is x plus k equal to f of this part. It will be x minus f of y plus k. And the next one is x plus k. And the next one is y. So here, if we use this part, again, left side is 2 times x plus k by this definition. Plus k equal to x minus, here we can write y plus k plus k plus x plus k plus y. And let's see how can we simplify negative y. We can cancel. Left side is 2x plus 2k plus k plus 3k. X plus x, 2x. Negative k you can cancel with k plus k. So if we subtract 2x, then 3k equal to k. If we subtract k, 2k equal to 0, and then k equal to 0. And because k equals 0, then we can see that from these things, f of x equal to x, and we've checked that it satisfies this equation. So k equal to 0, c equals 0, and it satisfies c, because look, we set c equal to this. When f of x equal to x, it is 0, so c is 0. So we've proved that our only answer for this problem is f of x equal to x. There are lots of also IMO problems you can try. Let me write some of them as homework. This one is IMO 2019. You can solve with these ideas. It is not hard problem. You can do it as homework number 1 for this problem. This problem as homework number 2. It is for PMO, last problem of PMO round 1. The difficulty I can say are the same. It is BMO 1, but the difficulty, because this is easy IMO problem. BMO 1, I think it was for 2019. I don't know, 2019, 2018, 2020. Try to solve also this problem. Also try to solve this IMO problem as homework number 3. It is again not hard problem. You should use replacement. And as I told you, there are around 20 important things in function problem. I told you some of them. With those you can solve these problems. If you want to learn the rest, I wanted to solve more IMO problems, PMO problems, USIMO, AME problems in functions. Feel free to send message to my WhatsApp number in the description comments. Okay. Let's solve problem number 7 of PMO 2023 national level. Okay. It says a set of positive integers is set to PLAC if it can be partitioned into two disjoint subsets f and t, each with at least 2 elements, such that the elements of f are consecutive Fibonacci numbers and the elements of t are consecutive triangular numbers. Find all positive integers n such that the set containing all the positive divisors of n except n itself is Pilek. Okay, let's write Fibonacci sequence. It is what it starts from 1, for example. 2, because we have 1, 1, you can start from 1, it's okay. 1, 2, 3, 4, sorry, sum of Fibonacci sequence is this. F1 is 1, F2 is also 1, sometimes they say also F0 is 0, and Fn equal to Fn minus 1 plus Fn minus 2, for n at least 2, okay? And the first terms of F00 and F11. You can say this definition, okay? Now let me tell you something. Here we can start from 1, because 1, 2, 3, 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13, 13 plus 8, 21, 34, and so on. Let's write triangular numbers here. Tn is n times n plus 1 over 2, okay? Or we can say sum of 1 to n. So T1 is 1, T1 is 1 plus 2, 3, 1 plus 2 plus 3, 6, plus 4, 10, plus 5, 15, plus 6, 21, plus 8, plus 6, 21, plus 7, 28, plus 8, for example, 36, plus 9, 45. Now, let's analyze this. It says, let's see, can we select 8? Look, it says we should divide the divisors into 2 parts, consecutive parts here, for example, here and here. Okay, something like this. If we select 8, then we know n is multiple of 8 and n is not 8 because it says except n itself. So if we select 8, the number, suppose for example 8 is in our subset, so n is multiple of 8. Then also 4 divides n. n is multiple of 4. But we don't have any 4 here. So we understand what? We understand that we cannot select 8. Okay? And let me tell you something. We should select 1 because 1 is divisor of n or n greater than 1. Because it says except n itself. So here we should select 1 to some parts or 1 to some parts. If we select here 1 to some parts, it's good because we can say 1, 1 or it says at least 2, 1, 2, 1, 2, 3, 1, 2, 3, 5. Here we want to see, can we say for example some elements like this one that we cannot select that to consider only finite number of cases. We said n is not multiple of 4 because we don't have 4. So for example we cannot select 28 because if 28 divides n, then 4 also divides n. And it's contradiction. It's contradiction. So we cannot select 28. And again 21 also. If we select 21, if 21 divides n, so 7 divides n. We should have 7, but we don't have any 7 here. So 21 is not also possible. What about 15? We have 5, 10, 2, 5, 6, 3, 2, and these things. So now we consider 2 cases. We select one from F or we select one from T. Let's consider here. If we select one from F, so case 1, we want to use 1 in F. So case 1, 1 is we select 1 and 2 only in F. Okay? So in T, if we consider T, it is in F and T. Okay, now here T we select because 21, 28 is not possible. We select from here or we select from here. Okay, because it's dot dot dot. If we select from this part, let's see. Because we've selected 1 and 2, you can start with 3. And look, if you select 10, because we've not selected 5 here, 10 is not possible in this case. So let's write the numbers. We have 1, 3, 6, 10, 15. 10 is not possible. Similarly, 15 is not possible because if you select them, then we need 5. But 5 is here, and we said from F, we only select 1, 2 in case 1, 1. In case 1, 2, 1, 2, 3. In next case, 1, 2, 3, 5. Okay. Now here, the only possible case to select is 3, 6. Okay, so if we consider LCM, n is multiple of 1, 2, 3, 6. It will be what? It will be 6. But n should be at least 6 because it says we shouldn't consider n here. So n is greater than 6. So n should be multiple of 6. So, for example, 6 times 2, 12 is not possible because we said multiples of 4 is bad. 6 times 3, 18. Then the divisor is 9. We don't have 9 here. It is bad. If we consider, for example, 4 times that, 24, again it's bad. So if we consider any other 6, for example, 6 times m, and m is at least, for example, 5, it is bad. Why? Because we've not, if we consider also 6 times 6, 36, it is bad because multiple of 4. M is at least 5 and m is odd because it shouldn't be multiple of 4 and m is at least 5. Now we should find m. M is a divisor of 6m and is not equal to n. So m is something, for example, here or here, but we should have consecutive terms. So if we select from, for example, this part, it is bad. Now we should see, can we select from this part? Okay, now let's start, for example, here, we know it is what? It is t times t plus 1 over 2. Suppose we've selected from some part here. It means what? For example, we've selected from, we know 36 is not good, 45, then it is plus 9, plus 10, 55, plus 11, 66, and so on. For example, suppose the first one you want to select is t times t plus 1 over 2. Okay, now here, t is odd or t is even? If t is odd, so you understand that t also is a divisor of, because then if t is odd, it will be t times t plus 1 over 2. You understand t is a divisor here. But we don't have t here because it is the smallest one. So t can be 3 or t is in f. Look, f is 1 or 2. T is 1 or t, because t is odd, t can only be 1. And the first one, it says 1 times 2 over 2 is 1. It's contradiction because we said it is after 45. If t is even, we can say it will be t over 2 times t plus 1. Again, t plus 1 is a divisor. It's not this. T plus 1 is 1 or 2. Then again t over 2 times t plus 1. And because t is even, so even plus 1 odd. So it can only be this. Again, contradiction. Okay? Because then t times t plus 1 over 2 cannot be greater than this. Now in next step, let's consider instead of 1 and 2 in f, we consider 1, 2, 3. Okay? So let's write this case. It is case 1, 2. Case 1, 2. So here we consider 1, 2, 3. And let's see what can we say. Here it is 1, 2, 3. We cannot select 1 here. We cannot select 3 here. 2 and 3, we have to select 6. Why? Because n is at least 6. N is greater than 6. Because if n equal to 6, we can't. Because we should select here at least 2 elements, 2 divisors of n that are less than n. So here we have to select 6. Because we have to select 6, what can we say we can't select from here? We should select consecutive terms from this board. So 6, 10. If we select 6 and 10, then we need 5. So we have problem here. We cannot select 10 because then we need 5. We cannot select 15. So again, in this case, we don't have any good case. If we consider case 1, 3, that we have 1, 2, 3, 5. So let's consider this part. So we can select 1, we can select 3, we should select 6, we should select also 10. Because, let's see. Does n is not 10 because n is also multiple of 3. So this divisor is less than 10 and n is multiple of 10 because 2 and 5. What about 15? 15 is divisor because n is multiple of 5 and 3 and n is greater than, because look, n is greater than equal LCM of 2, 3, 5 that we've written here. So it is at least 30. So we should select also 15. Now, it seems that 30 is a good number. Why? Because if you write divisors of 30, they are 1, 2, 3, 4, no, 5, 6, 10, 15, 30. We shouldn't select 30 because the problem says so. 1, 2, 3, 5, and 6, 10, 15. So 30 is the first good number that we found. Now let's consider case 2. Case 1 was what? That we use one that is in F. Now we want to use one that is in T. So if we do that, let's consider case 2, 1 in T. So here again you can select 1, 3, 1, 3, 6, 1, 3, 10, 1, 3, 15. So case 2, 1. If we select here 1, 2 only, 1, 3 only. So in this case, because we've selected only 1 and 3, here we cannot select 1, we cannot select 3, and because we cannot select 3, we cannot select this, we cannot select 2 and 5. So we should select something like this because we should select at least 2 divisors. So n is multiple of 3, so n equal to, for example, 3r. Now, suppose the first Fibonacci number that we select, for example, suppose it is x. And the next one is x plus 1. It is y. Okay. So what are the cases that we can consider? Because we can't select 2 here, so n is odd. Okay. Why we can't select 2? Because we can't select 3 here. So because n is odd, x is odd, y is odd. Now, and we can say something. GCD of x and y is 1. How can we prove it? Look, 1, 2, 2, 3, 3, 5. Suppose we consider 2 consecutive numbers. For example, GCD of fk and fk plus 1. If it is d, so because we know that fk minus 1 is what? Is fk plus 1 minus fk. So because d divides this one, then divides fk minus 1. So similarly, you can write it up to t divides f1. f1 is 1, so d is 1. So the x and y are relatively prime. So n is multiple of xy. And we know one of them is not multiple of 3. So if both of them are not multiple of 3, so n is 3xy times something. If, for example, x or y, 3 divides x or y, we know n is xy times something. So here, if, for example, 3 divides x, then you can say, okay, x over 3 is also divisor. But here x is the smallest one, so x over 3 should be 1 or 3. So in this case, x is 3, which is contradiction, because we have 3 here. In this case, x is 9. But we don't have 9 here, so both cases we reach contradiction. If 3 divides y, then what can we conclude? If 3 divides y, y over 3 is also divisor. I want to say y over 3 is less than x. I want to say y is less than 3x. The reason is this. Y is x plus z. And z is less than x. Okay? So y is x plus z. So it is less than 2x. So it is less than 3x. Okay? So, because y over 3 is less than x, y over 3 can be 1 or 3. Again, we can say, okay, y over 3 is 1 or 3. And again, we reach same contradiction. So for this part, we've reached contradiction now. In this case, 3 doesn't divide x and y. So n is 3xk times something. Now, because of this, we know that we have also 3x, 3y. So we should see 3x also and 3y. Here, okay, let's focus on 3x. We have x, we have y. Y is greater than x. The next one is x plus y is greater than x plus something greater than x, 2x. The next one is sum of these two things is x plus 2y. This plus this is greater than 3x. So 3x is not y because y is not multiple of 3 we said here. So if we want to see 3x, we should see 3x here. So it means what? X plus y equal to 3x. So y equal to 2x. But we said what? If y equal to 2x, y equal to what? Z plus x. It means what? It means z equal to x. But we know z is smaller than x in Fibonacci sequence. It is increasing. So again, here also we've reached contradiction. Now let's consider case 2 that we select 1, 3, 6. Okay, if you select 1, 3, 6 here, because 6 is multiple of 2, so we should select 2. But we shouldn't select 3, because we've selected 3 here, and we shouldn't select 1 because 1 is here. So again, it is bad because we should select at least 2 adjacent cases. Case 2, 3, we select 1, 3, 6, 10. So let's do this. If we select 1, 3, 6, 10, then what do we have? Again, we should select 2 because it's multiple of 2. We shouldn't select 3, we shouldn't select 1. Again, we have this problem. And also for case 2, 4, we have again this problem. That if we have 1, 3, 6, 10, 15, 2 is, we should select 2, we can't select 3, we can't select 1. So again, this case is also bad. So the only possible number that is good is 30, and we proved all other numbers are bad. If you had question about this, look again, we consider small example from 1, 3, consider cases, case work problems, which is so much useful in AME, USAM, or PMO. If you want to learn important ideas, background ideas, as I said before, feel free to send message to my WhatsApp number in the description comment. PMO National Level 2023, last problem of day 2, 8th problem. So it says, let S be the set of all points in the plane, find all functions f from S to real numbers, such that for all non-degenerate triangles ABC with orthocenter H, if f of A less than or equal f of B less than or equal f of C, then f of A plus f of C equal f of B plus f of H. So, for solving this problem, two things are useful. I will write as homework for you. One problem of BMO round 2. I think it was for 2019 or 2020. I will write problems and they help you to solve this problem. Okay, so let's analyze this. So here I draw an acute triangle. Suppose it is A, it is B, it is C without lots of generality. Suppose f of A less than or equal f of B less than or equal C. So suppose, for example, f of A is x less than or equal f of B, which is y, less than or equal f of C, which is z. And then we can say, okay, f of A plus C, first one, plus last one, equal to mid one plus f of h. Suppose f of h is also double. Another important thing that here we have non-degenerate means the area is not zero, means the vertices are not collinear. So here it is our h. If you pay attention, if you consider triangle BHC, can you tell me orthocenter is what? Look, it is our first altitude, second altitude, and third altitude. A is orthocenter. So one important thing that here we can understand, A is orthocenter of BHC, triangle BHC. Similarly, B is also orthocenter of triangle AHC, and C is also orthocenter of triangle AHB. Okay, now here I say, okay, X, Y, Z, W. W can be here, it can be here. So let's check. I can say, because X plus Z equal to Y plus W, if, for example, W be here, then if W, for example, is greater than Z, it's not possible. Why? Because Y is greater than equal to X, W greater than Z, so W plus Y will be greater than X plus Z. So W cannot be this part. Also, W cannot be here. Because then, look, X is greater than W, Z greater than equal W. So Z plus X will be greater than Y plus W. So the only possible cases for W is X. Let's consider this case 1. XW, Y less than or equal Z. Case number 2, we conclude X less than or equal Y. W, here Z. So let's consider these cases. For this one, our vertices are BHC. Okay. And we know it is A, it is H, it is B, it is C, it is A, f of A, it is B, it is H, it is C. So for BHC, For case number 1, let's first consider case number 1. In BHC, we know W plus that first one plus last one equal to Y plus X. Okay. And here, if we consider AHC, X plus Z equal to Y plus W, which is exactly this one. And third one, AHB, the first case, is X plus Y equal to W plus Z. Okay, AHB, X plus Y, W plus Z. AHC, X plus Z equal to W plus Y. ABHC, W plus Z, Y plus X. Okay, now let's analyze these cases. So, first one, we know X plus Z equal to Y plus W from first part, and this part, W plus Z equal to Y plus X. So if we subtract, we can conclude X minus W equal to W minus X. And then if we take this to left side, this to right side, 2X equal to 2W, so X equal to W. And when X equal to W, Y equal to Z. Okay, so let's check because of this equation. X equal to W, Y equals Z, X equal to W, Y equals Z, X equal to W, Y equal to Z. So it satisfies all equations. So let's consider. So we know what A was X. So H was W, F of this. So it should be also X. F of B, which was Y. Here we write Y, C also Y. And we know X is less than or equal Y because we said X less than or equal Y less than or equal Z. In first case, we've reached this. Now, let's consider second case. Okay, in case number 2, BHC, Y plus Z equal to X plus W, AHC, X first one plus last one, X plus Z equal to Y plus W, and last part, X plus Y. Here, AHB. AHB, X plus W equal to Y plus Z. Okay, so here again we say, okay, X plus Z. Okay, if you write first equation again, X plus Z equal to Y plus W. And here Y plus Z equal to X plus W. If we subtract, then we can say that X minus Y equal to Y minus X. So here we conclude 2X equal to 2Y. So we conclude here X equal to Y. And because X equal to Y, then this equal to this. Z also should be equal to W here. And let's see the equations. XYZW, XYZW, XYZW. Okay, so in this case, X equal to Y, Z equal to W. So if we draw the triangle, here we can say, okay, A is X, B is also X, so C is Z, and H is also Z. So in this case, as you can see, always the vertices, two of them equal, and for example, YY and the orthocenter equal to the last one. If all vertices are equal, it's okay. H equal to them. If, for example, we have two different numbers, we can't have three different numbers for vertices. We can have x, 2y, or for example, 2xz, and then the orthocenter equal to the thing that is left. So the thing that is left can be greater than them. Like here, z is greater than equal x. For example, if z and x are not equal, z greater than x. Here, y, 2y and x is less than y. So it's not important that the thing that is left, for example, here, x is less than or equal 1. Here, z is greater than equal x from first part that we've considered, x less than or equal y less than or equal z. So the thing that is left here, z, is greater than equal these two x's. Here, the thing that is left, x, is here, z that is left is greater than equal to x's. Here, x that is left is less than or equal to y's. So, okay. So we've concluded that for any triangles, two of them are equal. And if three of them are not equal, then h should be equal to the thing that is left. Okay, now one answer for this problem is all of them be equal to each other. For all, for example, x, f of x equal to a constant, for example, t, and it works. Okay, it is our first answer. Otherwise, so we have at least two different variables, two different f's. So suppose, for example, f of this part is a, f of this part is b, which a is not equal to b. By the thing we said, if we draw, for example, suppose we draw a perpendicular, we said if we consider any triangle and that, for example, we have like this, then this part, each term here is a or b. So, for example, all these lines are a or b. Also, let me tell you something. If, for example, we have acute obtuse triangle, as you can see in both cases, again, two of them are equal. Also here, two of them are equal. So, in this case, also let's consider for if you have right angle triangle. So this part is this, x for example equal to this. Let's see, we know the vertices here, x equal. And if you consider, for example, y, can all these things be different? Y, z, no, for example, suppose x is less or equal, y is less or equal z, then x plus z, if all of them be different, so x plus z equal to y plus x, which is impossible. If, for example, two of them same, here is good because it will be similar to other cases, but here, if you have x, y, and x and y are not equal, so you conclude that, for example, if x is less than or equal x less than or equal y, x plus y equal to x plus the orthocenter, so x equal to y. So we understand if you have right angle triangle, the case if all vertices are not equal, we should have x, y, y. Okay. Now here, if we consider this one, here we have a, here we have b. So all things on this line, like this should be b. Okay, all of them should be b. And if you consider also this line, all here should be b because of this a, b. And for this b, all things here should be a. Okay. And because of this point, if we consider another, let's see, if we draw another perpendicular, here we have b, here we have a, here we have, here we have b, here we have a, and this part should be a because of this part, but it is not b. So we've reached a contradiction. So we proved that it is not possible to have more than one variable. So our only answer is this. Let me again explain this part. This is special cases of this. We said if we have different variables on vertices, f of h equal to the thing that we have one from that. Okay, and three variables is not important for a triangle. So here, if we do the same thing, here f of h equal to this x. So if we have, so it should, if you have, if vertices are not same, so it is the thing that is left. So other two things should be equal, y, and here x, if x is not equal to y. And that's the reason we say if a, b here we have, if we consider a triangle here, it is a, these two things should be, because it is b, these things should be b. For all points here, we should have b. Similarly, if we consider this part and this part, for all things here, we should have a. So if we consider ab here, then by same proof, if we consider this part for this triangle, let me erase this thing. So again, it is b, it is a, it should be a. So it should be both a and b, which is impossible. So our only answer for this, for all x, f of x should be equal to t. And let me write the homeworks you need for this problem. Try to do this problem as homework number 1, British Mathematical Olympiad Round 2, 2020. You can solve it. It's related to H and useful similar ideas that we've used in this problem. Homework number 2, we Each point on a plane is red or blue. May I correct this part? Is red or blue? Prove that. Part A. There exists here an equilateral triangle such that the color of three vertices are equal. For example, part B, a rectangle such that again the color of all vertices equal. Okay, this problem has around 15 parts. Lots of things. Also IMO problem. If you want to solve all these types of problems from different books, each part is from a different book, from different exams. Also some part from IMO if you want to know. For some of the rest of that, you can try these two things. If you solved and wanted to solve the rest, feel free to send message to my WhatsApp number in the description and comments. Okay, look, we've considered many ideas here, homeworks from BMO British Mathematical Olympiad, other exams. If you want to learn all important ideas, formulas, you need to know 40, 50 important formulas in geometry, important ideas in combinatorics, like this one, number theory. For example, for this one also, we consider when we color with three colors. Again, we want to prove A, that problem is a two-step problem, two steps, and that's the reason it is a little high level with respect to this part. If you want, and so much harder than the problem of PMO, if you want to learn those ideas, as I said before, feel free to send message to my WhatsApp number in the description and comments. Thanks for watching this video, and take care, be safe, bye.